In this lesson, we'll talk about the properties and the naming of alcohols, and reactions that use alcohol as a reactant, and reactions that produce alcohol as a product. Alcohols are hydrocarbons that contain a hydroxyl group. These are functional groups with an OH compound. This OH is not to be confused with hydroxide. Hydroxide is an ionic compound, whereas a hydroxyl group is a molecular compound. The OH group provides the alcohol molecule with a polar molecule, as well as provides it with a hydrogen bond. Therefore, alcohols have a higher intermolecular force. Therefore, they have a higher boiling point and have a lower volatility than other hydrocarbons. A lower volatility means that they are less likely to evaporate. Short-chain alcohols such as methanol, ethanol, and propanol are soluble in water because the hydroxyl group gives the overall molecule a net dipole. Longer-chain alcohols such as butanol and pentanol are less soluble in water because their hydroxyl group is not sufficient to give the molecule an overall polarity. Medium-chain alcohols such as propanol are often used as solvents in organic reactions because one end of the molecule is polar and the other end of the molecule is nonpolar. Therefore, it is able to dissolve both polar and nonpolar compounds. The most simple alcohol is methanol. Sometimes this is also called wood alcohol because it is fermented from wood. It is toxic to humans, and drinking even very small amounts can lead to blindness or even death. Methanol has many industrial uses, such as windshield wiper fluids and antifreeze. Ethanol is also known as grain alcohol because it can be fermented from grains such as wheat and barley. And of course, it is this alcohol that is present in beer, wine, and spirits. Industrial applications include lacquers, varnishes, and perfumes, as well as gas-line antifreeze in the winter. As you have noticed by now, alcohols are named by simply dropping the E from an alkane and adding the letters OL. So methane becomes methanol, ethane becomes ethanol, and propane becomes propanol. If there is more than one hydroxyl group on the chain, we can indicate the positions of the OH group with the number 1 or 2 in the case of propanol. And we will give the hydroxyl group higher priority when we're numbering the carbons on the main chain. As well, if an alcohol has 2 or 3 hydroxyl groups, we have to indicate it with the name diol or a triol. Alcohols can be categorized into different groups based on the carbon to which the hydroxyl group is attached to. If the carbon to which the hydroxyl group is attached to has 1 additional carbons bonded to it, it is considered a primary alcohol. If the carbon to which the hydroxyl group is bonded has 2 carbons bound to it, it is considered a secondary alcohol. And if the carbon to which the hydroxyl group is bound to it has 3 carbons bonded to it, it is considered a tertiary alcohol. As we discussed earlier, it is possible to have more than one hydroxyl group attached to the hydrocarbon chain. The example here we have is ethane 1,2-diol, commonly known as ethylene glycol, which is windshield washer fluid. And we also have propane 1,2,3-triol, commonly known as glycerol, which is a common solvent, and it reacts with fatty acids to produce lipids in biological organisms. It is also possible for the hydroxyl groups to be attached to cyclic and aromatic compounds. Here we have an example of cyclohexanol, which is a cyclohexane compound with 1 OH attached to it. Notice that we do not need to indicate the position of the OH hydroxyl group because it is always at position 1. A special case of an alcohol is called a phenol, which is an alcohol group attached to a benzene ring. It is very prevalent in industry, so therefore it has a special name called phenol. If there are additional methyl branches attached to a phenol, we simply indicate those branches using a number, and because we give the hydroxyl group higher priority, the carbon to which the hydroxyl group is attached to is always numbered as position number 1. Therefore, this compound is called 2-methylphenol. Let's complete a few examples. To name the alcohol, first we have to identify the longest chain. Here is the longest chain, and because we give the OH group higher priority, we will number the chain from right to left. Now we notice that there are methyl groups at position 3 and 4, so this compound is called 3,4-dimethyl. There are 5 carbons in the main chain, so this is a pentane compound. But remember, we drop the E and add OL and indicate the position of the OH using a number. So the total name of this compound is 3,4-dimethyl pentane 2-ol. Similarly, for example B, we first identify the longest chain. We note that there are 4 carbons, so therefore this is going to be a butane derivative. In order to give the hydroxyl groups the lowest number, we'll number it from left to right. And we notice that there is a hydroxyl group at position 1 and at position 3. There are no alkane branches, there are no methyl or ethyl branches. Therefore, this compound is simply named butane 1,3-diol. The 1,3 indicates the positions of the hydroxyl groups, and the di indicates there are 2 hydroxyl groups on this compound. In our third example, we notice that there is a cyclohexane compound, and that there are 2 hydroxyl groups attached to it. It does not matter which hydroxyl group we number as number 1, we will still get 1, 3 as the numbering system. Therefore, the final name of this compound is cyclohexane 1,3-diol. Now let us draw the structural formula when we are giving it a name. We will draw the chain first. Therefore, propane, there's 3 carbons, 1, 2, 3. We note that as there is a methyl group at position 2, CH3. As well, there is a hydroxyl group at position 2. We fill in the rest of the carbons with the number of hydrogens required so that they have 8 electrons. And here is the structural formula for 2-methylpropane 2-ol. Similarly, for propane 1,2,3-triol, we note that there are 3 carbons in the main chain. There are no methyl branches or ethyl branches. However, we note that there are 3 hydroxyl groups, and they are at positions 1, 2, and 3. We fill in the rest of the hydrogens. And there is the condensed structural formula for propane 1,2,3-triol. Now let's talk about reactions that involve alcohol. First, we'll talk about reactions that have alcohol as a product. And these are additions reactions. If you remember, addition reactions are where unsaturated hydrocarbons, such as alkenes and alkynes, are reacted with small molecules to produce a alkane-like compound. For alcohols, this is produced by reacting alkenes or alkynes with water. And because we're reacting with water, this type of reaction is called a hydration reaction. When a water molecule is added across a double bond, you will get an alcohol compound. Now, because different branches can be attached to both sides of the double bond, different isomers could form. An example of an addition reaction is the reaction of ethene with water in the presence of a hydrogen catalyst to produce ethanol. Once again, the catalyst is a chemical that lowers the activation energy or speeds up the reaction, but is not used in the reaction itself. The opposite of an addition reaction is an elimination reaction. Here, a saturated hydrocarbon reacts to produce an alkene or an alkyne. For alcohols, this is known as a dehydration reaction because a water molecule is removed from the hydrocarbon. The water molecule comes from a hydrogen and the OH group on adjacent carbons. Adjacent means that are next to each other. The hydrogen removed is not a random hydrogen molecule, but it has to be next to the OH that is removed. Here we have the general example in the reaction of an alcohol in the presence of a catalyst, in this case hydrogen ions, to produce an alkene and water molecules. Specifically, we can say that ethanol reacts with hydrogen to produce an alkene, ethene, with water. Another type of a elimination reaction is called a dehydrohalogenation reaction. As the name implies, you will remove a halogen compound. Here we see that we have an organic halide reacting with a OH group to produce an alkene when a free hydrogen and a water molecule. Specifically, we can react 2-bromopropane with a strong base to give prop-1-ene, a bromide molecule, and water. Notice that not only are the number of atoms balanced in this reaction, the charges are balanced as well. On the left-hand side of the equation, we have a net charge of -1, and on the right-hand side of the reaction, we also have a net charge of -1. A third type of elimination reaction is called dehydrogenation. As the name implies, it is the removal of a hydrogen molecule from a saturated compound. It is most commonly done to ethane, so another name for this reaction is ethane cracking. A catalyst is used to increase the rate of reaction for the reaction of ethane to ethene with hydrogen also being produced as a product. Another way to produce ethene is by the dehydrogenation of ethanol. In fact, this was the way that ethene was first discovered. It was being heated in the presence of sulfuric acid, which provides hydrogen ions, which is used as a catalyst. Further experiments have determined that phosphoric acid and aluminum hydroxide can also be served as catalysts. And again, because water molecules are produced as a product, this type of reaction is a dehydration reaction.